Example number 6. Determine the z-transform of x sub 1 of n equals to 1 to the n and x sub 2 of n equals to a to the n using convolution property. Two right-sided signal, 1 to the n and a to the n. 1 to the n is my x sub 1 of n and a to the n is my x sub 2 of n. I need their z-transform using the convolution property. So let me make it happen using this property. The z-transform of x sub 1 of n will be x sub 1 of z equals to summation of 1 to the n times z to the negative n. Just plug in x of n equals to 1 to the n. My x of n is x sub 1 of n. What is my x sub 1 of n? My x sub 1 of n equals to 1 to the n. So just plug in 1 to the n here times z to the negative n. It equals to 1 over 1 minus z to the negative 1, which is ultimately z over z minus 1. The z-transform of 1 to the n times z to the negative n equals to 1 over 1 minus z to the negative 1. If I have 1 minus 1 over z here, and then you take the LCM of the denominator, at the end you're gonna have z over z minus 1. Look, it is a right-sided signal. If you remember, for the right-sided signal, this 1 is my outermost finite pole. So if you have 1 to the n, you're gonna plug in z minus 1. If there is a, you're gonna plug in a. If it is 2, you're gonna plug in 2 here. So since I have 1 here, so I will have z minus 1 here. It is the outermost finite pole for the right-sided signal. So this is gonna be the z-transform of 1 to the n. Now to find the z-transform of x sub 2 of n. The z-transform of x sub 2 of n will be x sub 2 of z equals to summation of a to the n times z to the negative n. Remember, my x of n is x sub 2 of n. I want to find the z-transform of x sub 2 of n. What is my x sub 2 of n? My x sub 2 of n equals to a to the n. Just plug in x sub 2 of n equals to a to the n here. So z-transform of a to the n equals to 1 over 1 minus a times z to the negative 1 equals to z over z minus a. Look, the z-transform of a to the n equals to 1 over 1 minus a times z to the negative 1. If I write z to the negative 1 equals to 1 over z, I will have a over z. And when you take the LCM of the denominator, you will get z over z minus a. Here I have 1, so I'm going to have 1 times z to the negative 1. So we don't need to have the product of 1 with the z, because ultimately 1 times z to the negative 1 equals to z to the negative 1. Remember, if you have 2 to the n, you're going to have 2 times z to the negative 1. If you have 3 to the n, you're going to have 3 times z to the negative 1. Since I have a to the n, therefore I'm going to have the product of a here, a times z to the negative 1. Now don't worry, I know you have a lot of confusions here, that how these two terms came. Don't worry, we're going to take many problems in problem solution section. You're going to learn that how we got this expression, this kind of expression. I have done everything there, but for time being, just take it as it is. I'm going to tell you in the problem solution section. So the z-transform of x sub 1 of n, which is 1 to the n, is x sub 1 of z, which is z over z minus 1. And the z-transform of x sub 2 of n, which is a to the n, is x sub 2 of z, which is z over z minus a. It implies that x sub 1 of z convolved with x sub 2 of z equals to z over z minus 1 into z over z minus a. The convolution of their z-transforms is actually the product of their final z-transforms solution. We have the product of z over z minus 1 and z over z minus a. So it equals to z squared over z minus 1 into z minus a. Look, z times z is z squared. Remember what we mean by the convolution. From the convolution we mean the product of the two signals. So x sub 1 of z convolved with x sub 2 of z means the product of their respective z-transforms, which ultimately equals to z squared over z minus 1 into z minus a. This is going to be the final answer for the two signals, which are x sub 1 of n and x sub 2 of n, using the convolution property. Now what will be the region of convergence? The region of convergence is z modulus is greater than a and greater than 1. Now look, both the signals are right-sided signals. 1 to the n is a right-sided signal, a to the n is a right-sided signal. So the z modulus must be greater than a and also must be greater than 1. When it comes to the right-sided signal, Z modulus must be greater than the outermost finite pole. For the first signal, my outermost finite pole is 1. So Z modulus must be greater than 1. We should go beyond 1, greater than 1, not lesser than 1. Similarly, for the second signal, my outermost finite pole is A. A is my outermost finite pole here. So Z modulus must be greater than A, because it is a right-sided signal. So when it comes to the region of convergence for the right-sided signal, Z modulus should be greater than the outermost finite pole. So Z modulus must be greater than 1, and Z modulus must be greater than A here. But what if I plug in Z equals to 1 here? 1 minus 1 will be 0. 0 times Z minus A will be 0. So I'm going to have 0 in the denominator, which is undefined situation. Similarly, when I plug in Z equals to A minus A is 0. 0 times Z minus 1 will be 0. So I'm going to have 0 in the denominator when I plug in Z equals to A. It is undefined situation. Therefore, Z cannot be A and cannot be 1. Should be greater than A, should be greater than 1, and also cannot be less than A and cannot be less than 1, because both the signals are right-sided. For the Z, which should be less than A or less than 1, is for the left-sided signal. Remember, we are not dealing with the left-sided, we are dealing with the right-sided. So this is my final answer using the convolution property with their respective region of convergence. When you look to this term, Z modulus is greater than A. One thing to be noted, when you look to this expression of the region of convergence, which shows that Z modulus is greater than A and greater than 1, which means that it is the intersection of the region of convergence for x sub 1 of n and the region of convergence for the x sub 2 of n. This region of convergence is the intersection of the region of convergence of x sub 1 of n and x sub 2 of n.